Welcome to another edition of Algebra You Can Do It. Today what we want to do is study radicals. Now, why do we want to study radicals? You might recall last time what we were doing is we were solving quadratic or higher degree equations. And the way we solve those quadratic and higher degree equations is we use this strategy. We put everything on one side, 0 on the other. We factored completely, and then we set each factor equal to 0. Now you might recall that there were times that there's some problems can't be factored any further. So our problem is, what happens if we're given a quadratic or higher degree equation that we can't factor by the methods we've shown you? Well, what we have to do is find some alternative ways of solving those problems. So that's what we're going to do, but we're not going to do it today. What I need to do today is to get you ready to solve problems a little bit differently. So today what we want to do is study radicals. And we want to show you how to simplify radicals. So let me come over here and talk to you about what I think most of you already know. You know, if I asked you, what is the square root of 25? I think most of you would say, gee whiz, square root of 25 is just plain 5. And what we've done there is we've taken the second root of 25. Or the square root of 25. Notice when the number up here is not written, it's understood to be 2. Now what we want to do today is show you how to manipulate with radicals and then show you how to simplify them. Now, how do you simplify square roots? Well, in order to simplify square roots, as usual, there's a strategy. And one of the strategies that it's always nice to know is to see how to rewrite something so we can simplify it. And the strategy we're going to use for simplifying radicals is, one, is to rewrite the number on the inside of the radical, which we call the radicand. We want to rewrite that as a product of a perfect square and some other number. Well, first of all, let's make sure we know that there are some that we already know the answers to. If I say to you, what's the square root of 36? You just say 6. If I say, what's the square root of 64? You say 8. If I say, what's the square root of 100? You say 10. But what happens if I say to you, what's the square root of 75? Well, you look at that and you say, gee whiz, I don't know. So what we're going to have to do is show you how to rewrite this so we can simplify that radical. And the way we're going to do this is we're going to use this strategy. We're going to rewrite this number as a product. In other words, we're going to rewrite it as a multiplication problem of a perfect square and some other number. So what we have to do is find a perfect square that's a factor of 25. Now the first thing that enters your mind is, what is a perfect square? So let's come right over here and let me write some numbers down. Let's just write 1, 2, 3, 4, 5, 6, and go down here to 10. Now, if I take each of these numbers and square them, what happens is 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, and I keep going down that process. 10 squared is 100. Now, these numbers right here, 1, 4, 9, 16, 25, 36, 49, 64, so on. These numbers right here are called perfect squares. They're perfect squares because the way I got them is I took a number and I squared them. I took this number and I squared it. I took this number and I squared it. So those numbers are perfect squares. So when I want to simplify a radical, what I have to do is take a look at a problem like this, the square root of 75, and I have to rewrite this as a product of some perfect square and some other number. Now a product means a multiply. So what number times another number gives you 75, where one of those numbers is a perfect square? And hopefully what you're saying is 25 times 3 gives you 75. 25 times 3 gives you 75, and sure enough, 25 is a perfect square. Now my question to you is, what is the square root of 25? And you say, hopefully, the square root of 25 is 5. You take that out, and what's left inside is 3. So if somebody said to you, let's simplify the square root of 75, what you would do is you would rewrite that as 25 times 3 and find out the square root of 25 is 5. You take that out, you're left with 3. Now, you're saying, let's do another one because I'm not quite sure. So let's do this one here, the square root of 32. Now, if somebody says to you, what is the square root of 32? And you say, gee, I don't know. So what you have to do is rewrite this as a product of a perfect square and some other number. Well, what I'm going to do is I'm going to come back over here to my perfect squares and say, gee whiz, I want to break 32 up into factors. So 25 is less than 32. Does 25 times some number give me 32? You say no. Does 16 times some number give me 32? And the answer is yeah. 16 is a perfect square. So I come back over here and I rewrite 32 as 16 times 2. Now again, when I don't know the square root, I rewrite the radicand as a product, as a multiplication problem of a perfect square and some other number. Now, do you know the square root of 16? And you're saying, yes, you do. That's 4. So I take the 4 out, and I'm left with 2. So that's 4 square roots of 2. Now, what we're going to be doing in a couple of days, in a next lesson or two, is we're going to be coming across problems, quadratic equations in particular, that we can't factor. So what we're going to have to do is use some alternative method in terms of solving the problem. And one of the things that we'll need in order to use that alternative method is to be able to simplify radicals. So let me come over here and I'm going to give you another radical and see if you can't simplify this radical. And Tommy, we'll give them about 20 seconds to get this one done. Okay, here's this one here. Let's try you simplifying the square root of 80. A little music there. Okay. Okay, now as you look at that, this is what some people might do. They might say, gee whiz, a square root of 80. Well, I can rewrite that as a product. That's the same as 4 times 20. And then they say, gee whiz, the square root of 4, what does that equal to? And you say, gee, that's equal to 2. So you take that 2 out and you're left with the square root of 20. Now at that point, some students might think they're done. But what you have to be aware of is that 20 can still be broken down. We can still rewrite 20 as a product of a perfect square. So what I'm going to have to do now is take 20 and realize 20 is 4 times 5. So there's that 2. Now the square root of 20 is 4 times 5. What's the square root of 4? And you say, gee whiz, the square root of 4 is 2. So I take this out with that 2, and 2 times 2 gives me 4. And I'm left with the square root of 5. So this answer is 4 square roots of 5. So as we do this problem, we say, gee whiz, that took a lot of steps. Does it have to take that many steps? And the answer is no. If you had realized that 80 could have been broken down differently, in other words, instead of writing 80 as 4 times 20, we could have said the square root of 80 is going to be 5 times 16. 5 times 16 gives you 80. And what's the square root of 16? And you say it's 4. So I take the 4 out and I'm left with 5. So that answer is 4 square roots of 5. Now notice we get 4 square roots of 5 doing it this way, and we get 4 square roots of 5 doing it that way. Okay. What's nice to know is the fundamental theorem of arithmetic tells you that we can break this number down no matter how we do its prime factorization, whether we do 4 times 20 and break it down that way, or 5/16, that any composite number can be written as a product of primes in one and only one way. So it doesn't matter if you said 5 times 16 to 4 times 20, you would eventually get the answer. What's the key in doing these problems? I would tell you that if someone asked me to find the square root of a number or to simplify a radical, what I would do is I would use the largest perfect square that's a factor of 80. Now notice 16 is a big perfect square, and 4, while it's a perfect square, is smaller. It's kind of like going up to kids and they might have a problem like 24 over 36 as a fraction problem, and we say reduce it. You have some kids that will reduce it by 2 and get 12 over 18. reduce that by 2 and get 6 over 9, reduce that by 3. And in other words, they keep going through the process where somebody else might take 24 over 36 and say, gee whiz, 12 goes into both of those, and you get the answer of 2/3. So rather than doing it as we did up here in a number of steps in reducing 24 36, we realize if we use a larger factor, we can do the problem faster or in less steps. And that's exactly the same thing over here. Somebody gives me the square root of 80 and you break it down using a small perfect square, it's going to take you a few extra steps. If you use a larger perfect square, it will take you a few less steps. Now, are you excited about that? I'm kind of hoping you are, because that's what we want to do when simplifying radicals. Now, what we'll notice is this, is when I have a problem like some perfect square, so let's say I have a problem like the square root of 27, and somebody says simplify that, well, what I need to know is the square root of 27 can be written or rewritten as a product of a perfect square and some other number. So remember, 27 is a perfect square. Now, what's the square root of 9? And you say 3. And what's left inside? And that is 3. So the answer is 3 square roots of 3. Now, if we look at these and examine this closely, what we find out, if I take the nth root of m times n, in this case, I'm just going to work with the square root. So the square root of m times n, that's equal to the square root of m times the square root of n. So we have the square root of m times the square root of n is equal to the square root of m times n. And that way, when we have problems like the square root of 54, what I'm going to do is I'm going to rewrite that as the square root of 9 times 6, which is equal to the square root of 9 times the square root of 6, and the square root of 9 is 3. So this answer is 3 square roots of 6. So what we have here is a little property that you may have had to learn in your algebra class. The square root of mn is equal to the square root of m times the square root of n. Now, I bring that up for a reason. Sometimes someone might say, what if I have the square root of m squared plus n squared? So I have an addition problem. Is that equal to the square root of m plus the square root of n? Well, the easiest way to make that determination is let's substitute a problem. Let's say I had something like 3 squared plus 4 squared, the square root of 3 squared plus 4 squared. Now, what do we know that this is 9 plus 16? That's the square root of 25. And what's the square root of 25 equal to? And you're saying 5. So the square root of 3 squared plus 4 squared is equal to, if I multiply that out, that's 9 plus 16, which is 25, and the square root of 25 is 5. Now, can I just break that apart and say the square root of 3 squared is 3, plus the square root of 4 squared is 4. 3 plus 4 is equal to 7. Does this hold up? Does the square root of 25 equal 7? Does 5 equal 7? And you can see this is not true. So the question that we had originally that we wanted to know, does the square root of the sum of squares equal the square root of each of the numbers? The answer is absolutely not. And why not? Because it doesn't work. So what we're going to be doing then is just working with radicals so we can simplify problems when we're solving quadratics. Now, if this is the methodology that works for finding perfect squares, what do you think it would do for finding perfect cubes? Well, what we would do is would write our numbers down, 1, 2, 3, 4, 5, all the way down, again, as far as we wanted to go. And now we would cube these numbers. Now, if I cube these numbers, I get 1 cubed is 1, 2 cubed is 8, 3 cubed is 3 times 3 times 3, which is 27. 4 cubed is 4 times 4 times 4, which is 64. 5 cubed is 5 times 5 times 5, which is 125. And I'd continue that process as far as I wanted to go, down to 1,000, or whatever. Now, if somebody were to say to me, let's simplify a third root, what's nice about math is I'm going to use the same strategy. I am going to find a number times itself 3 times. That will give me that number. So let's say somebody says to me, what's this cubed root of 27? Well, what I do is I look for 27 from my perfect cubes, and do I have it? And you say, yes, I do. And what number cubed gives me that? And you say 3. So the cubed root of 27 is 3. If I said, what's the cubed root of 64? Now notice to write the cubed root, I must put the 3 up there, so we know it's a third root. And I look under my perfect cubes right over here, and do I have the number 64? And you say, yeah, you do. And what number is cubed to give you that? And you say 4. So the cubed root of 64 is just plain 4. Now the question is what if that number is not on our chart? Let's say I had the cubed root of 54. So I come back over here to my chart, right over here, and I say, do I have a 54 here? And you say no. So what was a strategy for simplifying square roots? For simplifying square roots, we rewrote the radicand. We rewrote this number as a product of a perfect square and some other number. Now, since we're working with cubed roots, we have to rewrite this number as a product of a perfect cubed and some other number. So is there any perfect cubed that is a factor of 54? And hopefully you're saying 27. So this is 27 times 2. So 54 is 27 times 2. Now, what's the cubed root of 27? You go back and look at your chart, you find out it's 3, and you're left with the cubed root of 2. And I can continue that process for 4th roots or 5th roots or 12th roots or nth roots. That process continues to work. Now, are you excited about that? I'm hoping so, because we're going to be working with, in particular, square roots when we go back and solve equations, quadratic equations in particular, that we can't factor. So let's see if I give you this problem, if you can't go ahead and simplify it. Let's see, what if I say to you, simplify the square root of 40? Okay, about 10 seconds worth of music, Tommy. Okay, now in simplifying this, somebody might say, well, gee whiz, this is 8 times 5. Now, is there any problem with saying the square root of 40 is 8 times 5? And the answer is no, that's okay. But if you do it that way, it's going to make a real long problem. Now, what happened or what went wrong here, or why would it be a long problem? Well, when you simplify a square root, now remember when we have a square root, we don't have to write the 2 in there. What you want to do is you want to rewrite this as a product of a perfect square and some other number. Notice that neither 8 nor 5 are perfect squares. So if you rewrote 40 as 8 times 5, you just created some extra work for yourself. So let's not do it that way. What other way can we write down 40 as a product of a perfect square and some other number? And hopefully what you're saying is that is 4 times 10. 4 times 10 gives you 40. Now, what's the square root of 4? And you're saying, gee whiz, the square root of 4 is 2. So that's 2. And what's left on the inside? 10. So if I want to simplify the square root of 40, what do I have to do? I have to just break it down into a product of a perfect square and some number and take the square root of the perfect square. So that answer is 2 square roots of 10. All right. Now, why are we learning this stuff? Because just in 2 more lessons, we're going to have a formula that looks like this. And what we're going to be asked to do is simplify the number within that radical. We're going to be asked to simplify that square root. And what's going to be important to you is you're able to, with your other mathematical knowledge, in terms of working with positive, negative numbers, and then taking square roots and using substitution to simplify that expression. So let's say that I said that B was 10, A was negative 2, and C was equal to 3. And I said, with this information, let's plug that number in, let's plug these numbers in and simplify. So what we're going to do is this. Everywhere we see a B, we're going to put 10. So it's going to be 10 squared minus 4, A is negative 2, C is 3. So I have my B squared minus 4AC, and A was supposed to be negative 2, so let me put that negative in there. It's always nice to copy the problem correctly. Okay, now in simplifying this, what I have to do is, can I take the square root of 10 squared and just call that 10 right now? And you're saying, no, we've already discovered that. So I'm going to simplify that. That's 100. Now, I have negative 4 times, well, what I have here is minus 4 times negative 2 is negative 8, times 3 is negative 24. So I have 100 minus a negative 24, which is the square root of 100 minus a negative 24. When I subtract, what do? I change my sign and add, so that's positive 124. So what I have right here is a radical, the square root of 124, and what we need to do now is be able to simplify that radical. Okay, now do you think that's something you can do on your own? You're immediately looking at that and you say, gee whiz, I'm not familiar with numbers like 124, that's a large number. So what you got to do is some trial and error. You want to rewrite this as a product of a perfect square and some other number. So let's see what we're going to do here. How can you break down 124? Well, do you see any numbers in there that you recognize? Let's go back to our perfect squares. Okay, the numbers that we don't have, 7 squared is 49, 8 squared is 64, 9 squared is 81. Now, does 81 go into 124? The answer is no. Does 64 go into 124? The answer is I don't think so. Does 49 go into 124? And the answer is I don't think so. Does 36 go into 124? And you're going, gee whiz, I don't know. Well, let's see. If I take 124, can I rewrite that as 36 times some number? 36 times 4, does that work? 4 6 is a 24, 4 3 is a 12, that's 144. So that answer is no, 36 doesn't work. Does 25 work? And the answer is no. Does 16 work? Well, let's see. 124 is 16 times some number, give me 124. Well, again, we don't know, so we might have to divide 16 into 124, and what do we get? 9 sixes of 54, 9 ones and 9, and again, that's too big, so that doesn't work. So we're trying, and we're having problems with this one because we're not familiar with the number. That's not a problem. So I'm going to go to the old standby, 124. I know 4 goes into it. 4 is a perfect square, so I'm going to rewrite this as 4 times 31. 4 times 31 gives me 124. Now, notice, because we were not familiar with 124, that took a little extra time. Okay? Now, does everyone see 4 times 31 gives you 124? What's the square root of 4? You say 2. So that I take the 2 out, and I'm left on the inside with the square root of 31. So, if I were to have given you this problem here, if I said, evaluate this expression, the square root of b squared minus 4ac, with this information down here, with b equaling 10, a equaling negative 2, c equaling 3, what I would do is I would substitute carefully, okay, plugging those numbers in, simplifying, and then we have to rewrite that radical. Big time problem. The more familiar you are with the numbers, the easier it gets. And what we're going to be doing, just in, like I said, in a couple of short lessons, is we're going to be simplifying formulas that this thing right here is a part of. So let's try one on our own. Let's say that I give you this information here. A equals 1, B equals 5, and C equals negative 2. Tommy, about 20 seconds, and let's see them plug that into b squared minus 4ac, the square root of that. There you go. Okay, now what you would have to do is when you see that expression, everywhere you see an A, B, and C, plug those numbers. So we have B squared, that would be 5 squared, minus 4 times A, which is 1, times C, which is negative 2. Simplifying that, that is 25 minus 4 times 1 is 4 times 2 is negative 8, minus 8. And 25 minus a negative 8, that is 25 plus 8, which is 33. And the answer is the square root of 33. Now your job would be is, can you simplify that? Could you rewrite this as a product of a perfect square and some other number? And it turns out in this particular one, you cannot. So what's going to happen? In a couple of lessons, we're going to be having a formula that's going to include this thing right here. And what you're going to need to be able to do is simplify that radical. And the way you do that is you're going to combine these terms, continue to combine them, and then you're going to simplify this radical here if possible. Now notice on the radical over here, we're able to simplify this by rewriting this as a product of a perfect square and some other number. So simplifying radicals, is it difficult? The answer is no. Why are we doing it? Because later on we want to solve quadratic equations. See you next time. Bye-bye.